Okay, so in this problem on group homomorphisms, we're given a function from z4 to z4, and we're told exactly what it does on every element. It sends 0 and 2 to themselves, and it takes 1 and 3 and it swaps them around. And we're asked to understand whether this function is a group isomorphism. So maybe just make a little checklist of all the things we need to know in order to know if we have a group isomorphism. What are some things we need to check?
So the identity should be sent to the identity.
Okay, we should check that the identity goes to the identity. Let's just make the whole checklist first, and then we'll think about them.
Okay.
What else do we need to check?
And also the thing that if we break the things in the parentheses by the operation of a group, it still works.
The homomorphism part.
Yeah.
So we want something like phi of AB equals phi of A times phi of B. Okay, what else do we have to check to get an isomorphism?
Maybe we want like phi of A star B equals phi of A
dot
phi of B, because we are supposed to have like two kinds of operations, or they can be the same operation, but it can also be two different ones. Okay.
And then
dot
here,
A dot B, I think.
Dot B.
Yeah.
Right here we want to be careful because in Z4 we usually write the operation as plus.
So it's
so
just
maybe
plus
it's
here.
better to use this other notation. Okay, what else I have to check then? Do I have a group isomorphism?
So by jectivity,
Yeah,
which
okay.
is
So I
injective
guess
and surjective.
injective and surjective. Let's put them down separately. Is that everything?
I think so.
Yeah, I think that's everything.
Okay.
Let's do the easy ones first. What are the easy ones?
The first one, identity to identity, because we're given.
Oh, look, there it is.
Yeah.
Great. That's convenient. What else is easy?
I think injective and surjective should be easier.
Pretty easy. Look, there they are. Here's all the elements of Z4.
Yeah.
And
so
they
because
each got hit by one thing.
yeah, and everything has everything in the output has an input. So
yeah, we wrote down all the outputs, and we wrote them down as many times as they showed up, and they all showed up exactly once. So showing up at least once is surjective, showing up no more than once is injective. Okay, so we really just have to check this last property.
yeah.
I want to show that if I take two of these things and I add them together, right, it's plus, I guess, equal phi of A plus phi of B.
So if at least one of the two things is 0, it's very like obvious. It
That's
holds.
true.
Yeah.
Okay. So we're just going to do this sort of by a lot of case analysis, maybe. It's also okay if they're both equal to 2.
Yes.
Because 2 doesn't change. Phi is just the identity.
So basically we just need to check the cases where at least one of A and B is 1 or 3, I think.
Yep. Okay, so we need to check what happens to 1 plus 3. We need to check what happens to 1 plus 2. And we need to check what happens to
2 plus 3.
2 plus 3.
I think that.
Is that all?
I think so. Because we don't care about zeros anymore because we already checked them. So.
Oh no, we have to check 1 plus 1.
Oh, you're right. And 3 plus 3.
And 3 plus 3. Okay, so there's 5 things to check. Five things is okay. So let's see. This is 4. Phi of 4
which is
is
0.
0. So that's 0. And what if I take phi of 1 and phi of 3?
That is
That's
0.
fine. That's also adding up to 4.
Yep.
Okay. 1 and 2. That's phi of 3. Phi of 3 is called 1.
Yeah.
And is that in fact equal to phi of 1 plus phi of 2?
Yes. Because that's 5, which is 1 gives you 4.
Okay. Here we have phi of 2 plus phi of 3.
So that should be 3.
Looks like 3. Either way you
Which
do
is,
it.
yeah.
Phi of 1 plus 1, that's phi of 2, this is called 2. And phi of 1 is 3, so I want to know, is that the same as 3 plus 3?
Yeah.
3 plus 3 is 6, which is 2, mod 4. And finally, 3 plus 3 is 6, so this is called 2. 2 goes to 2. And if I instead compute this, then I'm computing 1 plus 1.
That is 2.
That's definitely 2.
Oh, great.
All right. Wow, so that was not the most elegant thing to work out, but it's a small enough group that we could just compute everything in sight and know that we have a group isomorphism.